have been discussing quantum Hall effect, which happens in a 2-dimensional electron gas at very low temperatures in a very clean system and under a perpendicular magnetic field, which is fairly large. Typical magnetic fields are 20 Tesla, 30 Tesla and so on and temperatures are as low as 1 degree or even less, 1 degree Kelvin or less. So, so what I said was that the electrons first have to be confined and confined in one direction, so that they become 2-dimensional, the carriers become 2-dimensional carriers, they move in only in 2-dimensional. So, let me show you how it is done. So, the geometry of this device is this, that let me draw it. This is a MOSFET geometry, MOSFET configuration, and there is a source and there is a drain here. Sorry. The okay, and there is a silicon dioxide layer, SiO2, these are also SiO2, these regions are also SiO2. Then you have this source and drain, these are the source and drain. These regions are source and drain. Okay. And so, what you do is that you apply a here, and then on top of this you put a aluminum metallic aluminum, and this acts as the gate. So, this is the V gate that you apply here, okay. And this is in this case this is positive with respect to this. Okay, so, this is the configuration from here one drains out. So, this is the typical and this is p type silicon. So, because of this configuration you will have a n plus layer here, a n plus region here, and there is a confinement of electrons of the carriers in this region just below this SiO2 layer, and they are confined. I will show you why and how they are confined. So, the axis is such that the downside is Z. So, this is my aluminum gate. Okay. If I draw the energy diagrams in this system, so let's just draw it. This is my aluminum gate, this is the SiO2 layer, and then there is a region, and is called inversion region, and there is a depletion region ZD, which is like this. And what you are doing is that okay, let me just plot first and then I will show you what I mean. Okay. So, I have this valence band bends and the conduction band which is like this, and this is where the EF is. Okay. So, this is somewhere the Fermi energy is. Now, you put the gate voltage. So, there is a Vg at here in this here at the aluminum. So, that you can now move this Fermi level up and down, or other way to think about it is you can move these conduction and valence bands up and down. The better way to look at it is that we move the Fermi level up and down by doing this. Now, the valence band, since this region of the conduction band has come below the Fermi level, and it is a region of and the potential. So, why does the potential look like this? Earlier, before I applied a gate voltage, the potentials were straight horizontal lines. These C and V were horizontal lines, whereas now what has happened is that minus, because of the electric field coming from the gate, you have to solve this equation. This is equal to your electric field. So, there is a field inside, that field bends these bands, and so the bending happens because this electric field is constant, and your V then is V equal to 0 to Z. See, at 0 the value is the same as Vg, then E times dz. Okay. So, what you get is EV EC then goes to EC minus E times Vg minus Zd, and EV goes to EV minus E times V minus V means Vg, at 0 it is Vg minus Zd. So, that means there is a proportional to Z change. So, the whatever potential was there, suppose this was the potential, and now you apply another one which is like this. So, the net effect is a potential like this. Okay. So, that is the way the bands are bent, and then the electrons get transferred from here to here, and these are the electrons which remain confined within this distance. Okay. So, that confinement is what has to be achieved within a few nanometers or so, depending on the other parameters of the system. So, that is how the confinement works. Okay. Okay. So, once the confinement is achieved, the rest is basically very simple. We have to solve something called a Landau problem. So, these are called Landau levels, and it is basically 2D electron gas. So, that means it is confined in one direction, which is Z here for us, electron gas in a strong magnetic field. Strong is required for the experiment, but Landau problem you can do it any magnetic field. So, that is the problem that one needs to solve now. Okay. See, the B is basically a vector which is 0 0 B. Okay. Only the Z component exists and its value is B. Now, we know how to solve the Schrodinger equation for such a situation. How does one do it? The way to do it is that see, the other thing that one assumes is that the spin degree of freedom is already frozen, because the magnetic field is fairly high. So, the spins have all aligned along the direction of the magnetic field. So, we will not bother about the spin part of the Hamiltonian, that will not give us any new result. So, then only the orbital part is necessary. So, P we know under magnetic field goes to P minus E A by C, right. So, E here is of course negative, and the other thing that we have to use is B, where B is equal to curl of A. Okay. So, this is the vector potential that we have all done in our electrodynamics, and P minus E A by C is the canonical momentum in presence of a magnetic field. So, in this we have to just incorporate into our theory. So, for that we need to know what A is. A of course has, we remember that your electrodynamics, you can have a choice of E, which is you can choose in several ways. There is a freedom of gauge choice. So, one choice which is so A you can choose as minus Y B 0 0, or you can choose in another way 0 x times B 0. So, both the choices are perfectly all right. This is called the Landau gauge. There is another way you can also do is something called a symmetric gauge, which you can choose as a combination of both, keeping both of them for your A. So, symmetry gauge for example is minus half minus Y B x B 0. So, this is y times b, x times b and 0 of course. So, this is called the symmetric gauge. You can work in any gauge you like, and different books or different notes you will find work in different gauges, and we will not discuss much of it. We will choose one particular gauge, which is the first one that I have written down, this one, and we will stick to that. For example, this one chooses this example that this view graph chooses the other gauge, that the y component is to be x times b, okay. But it does not matter, because the results do not depend on the choice of gauge. The final results will not depend on the choice of gauge. In fact, the symmetric gauge is also a very popular choice. The algebra becomes interesting in that. So, in if you do this, then just replace the way to do is now is P. Now the charge is negative, so P plus E A by C. For P, you replace minus I h cross grad. Okay. So, if you do that, then of course, you will get back your Schrodinger equation. That is what the Schrodinger equation will look like now. So, let me just write down the result that you will get in the gauge that I have just informed. H cross square by twice m into I del x plus E b by H cross c into y minus del 2 y del 2 y. So, let me just write del x instead of del x. And del 2 del y 2 times psi equal to E psi. Okay. So, that becomes your Schrodinger equation. Remember, this z component is just a free fermion, because it is sorry, the z component is confined, and in that direction you do not have motion of the electron. So, you are only concentrating on the x and y direction, and that is the way this thing is set up. Okay. So, for example, remember the Hamiltonian still, as this says, in our case the Hamiltonian has transition symmetry in the x direction. Okay. Okay. So, if this is the Hamiltonian, then you can choose a wave function. A trial choice is not difficult to make. It is some constant e to the power I k, sorry about it. E to the power I k x some phi times y. This is called the separation of variable. You have done it in hydrogen atom problems or in many other cases. So, what one does is that one chooses a plane wave function along the x direction, because the transition symmetry exists in that direction still, and so one keeps that intact and write a plane wave state along the x direction, whereas in the y direction, of course, you have to be careful, because there is a term which will change the nature of the wave function, and what will happen you will just see. So, then you can just put this solution in, put this trial wave function in this, and what you will land up is h cross omega c by 2 minus L square del 2 del y 2 plus y by L minus L k, this is that k square into phi y, this is h cross omega c equal to E phi y. So, this is what you will get, where L is L square is h cross c by E b. So, that is called, that is the magnetic length. This is also written generally as L sub m to make it to explicitly mention that there is this is a magnetic length. It, as you can see, that these h cross c and E are all fundamental constants, and it is only inversely L square is inversely proportional to b. So, this defines a new length scale in the problem. Okay. It is interesting that from the algebra in a magnetic field, transverse magnetic field, a new length scale has now emerged in the problem, and that length scale is dictated by the strength of the field. The stronger the field, the if you increase the field, the length scale decreases as a square root. Okay. So, that is the that here also you can see on the this that L is C has been taken to be 1 in this calculation, but the as you can see the result does not change in which gauge you work in, and the length is h cross c by E b. This is the magnetic length. Now, if you look at this Hamiltonian that you got this equation h psi equal to E psi, the left hand side represents a simple harmonic oscillator in one dimension. Suppose L this k was 0, then this would be just a simple harmonic oscillator, right. So, so that tells us that this problem has an interesting symmetry, that it becomes a simple harmonic oscillator problem in one direction and a plane wave in the other direction. So, the solution then appears to be can be written off, and remember that because k this term is non-zero, the basically the center of that the oscillator has just been shifted from y equal to 0. So, that is the amount of shift L square k. So, the center is away from 0 by amount L square k. So, one can write down the solutions, and solution is basically a simple harmonic motion in one dimension, simple harmonic motion in y direction, and a plane wave in the x direction for my choice of gauge. And for this one, for example, it is just the other way, it is a y along y direction, they have a this has a plane wave, and along the x direction it has a displaced harmonic oscillator. That is all. I purposely chose this example just to show you that two gauges do not differ in their final result. The solution remains the same, only the x and y gets interchanged with a minus sign plus to minus, as you have seen that choice of gauge also involves a sign. Now, what does this lead to? Well, this leads to so wave function of the form phi n k. What this n is, I will tell you, equal to some constant, some. This is a Hermite polynomial. Remember your simple harmonic motion, y by L minus L k e to the power exponential minus y minus L square k square by twice L square. So, this is the one can write it as e to the power, then you can see the similarity clearly that this is a e to the power minus y minus L square k. So, had this part not been there, this would just be e to the power minus y square by 2 L square, which is a simple harmonic oscillator with origin at 0, where now you have the origin shifted by an amount L square k. So, that is the that is the solution, and the energy, this n comes from this sorry about it. This n k is actually independent of k h cross n plus half, and this n is an integer. Omega c as before is E b by m c. So, h cross omega c is the scale of energy. I mean, this is exactly like a harmonic oscillator. So, the harmonic, it is like there is this 0 point energy at n equal to 0, you will still have a finite energy, as happens in any confined potential, for example, and oscillator potential is a confining potential. And h cross omega c into n plus half has the same form that you get from the Landau, from the oscillator. So, that means that the energies are quantized in this form, that energy at as a function of, this is density of states written, but if you write the other way, which is so let me just draw it the way we normally draw. E is basically a series of lines which are separated by an amount h cross omega c, and there the separation is constant, goes on and on and on. Now, this x axis, let me just keep it for the time being, but this is just the energy. Look at the energy, and this is how it pans out. The result tells you that this is how it this discreteness of the energy as just like a harmonic oscillator. The interesting thing is that this is the way, if you just divide this by h cross omega c, then these will be 1, 2, 3, 4 and so on. Now, if you have b equal to 0, then of course, this will not happen. This will be just the 2 dimensional case, where we know that the 2 dimensional free particle case, right, with the density of states which is constant. Okay. So, this plot on the left, for example, gives you the density of states as a function of energy, and as you can see that there are fixed energies at which there is a finite density of states. The density of states calculation is important here, because the number of states here depends on the degeneracy of this level. So, that degeneracy needs to be calculated, and this that we will do in the next class, where we will try to understand the quantum Hall effect in terms of these degeneracies of these levels and this level diagram. The right hand side is actually the picture that you really get in real life, in real systems. This is of course the mathematical theory, the Schrodinger equation solution gives you on the left hand side one, but real systems always has disorder, imperfections. So, the relaxation time being very large, almost infinite, cannot be true, and then there are always scatterings, and that scattering will develop, will lead to some width of each of these levels, and that is the real life picture. But even then, if your H cross omega c or magnetic field is fairly large, then the width can be much smaller than the gap, which is H cross omega c, and you can still treat these as discrete levels with of course a large degeneracy, which I will calculate in the next class, and that leads to the quantum Hall effect, the integer one.